Welcome to Norton Chemistry. Today we'll be answering 2021 Paper 1 for A-Level Chemistry OCR A. Let's get straight into the multiple choice questions. Usually I'd recommend answering the long form questions first, but for the purposes of this video I'll just do the multiple choice questions first. So question 1. Which statement describes electronegativity? So let's first read through the answers and then decide. A measure of the reactivity of an element, the ability of an atom to attract an electron to become a 1- ion, the attraction of a bonded atom for the electrons in a covalent bond, the attraction of an atom for a lone pair of electrons. So electronegativity is answer C, because it's the attraction of a bonded atom for the electrons in a covalent bond. So when you have, for example, a covalent bond between two chlorine atoms, they have equal electronegativities. So they both attract these electrons here equally. Question 2. A chlorate ion has a 1- charge. What is the formula for sodium chlorate VII? So these are Roman numerals. So VII we know is 7. So that means that the oxidation number of the chlorine in the sodium chlorate compound is 7. So we need to look through our answers and identify which of these compounds has a chlorine atom with a oxidation number of 7. So our oxygen atoms are going to always be -2 unless they're bonded to fluorine. So for example in NaClO3 -2, so if we multiply that by 3 we get -6. Sodium is always going to be +1, so then we can simply deduce that it will be a +5 chlorine charge, so it's not that one, and therefore if we work out for B we get a oxidation number of +7, which is the correct answer. And then question 3. The unbalanced equation for the reaction of silver with concentrated nitric acid is shown below. So we have gold, nitrate ions, H+, which form Ag+, NO, and H2O. Which numbers for Ag and H2O will balance the equation? So to answer this question, you want to, because it's multiple choice, the easiest way to do it is probably just to trial all of the numbers and see which balances the equation. So if we put 1 for A, if we put 1 for Ag and 2 for H2O, we have to ask, does that balance the equation? And it balances for Ag, balances for nitrogen, it balances, but however it doesn't balance for oxygen because you've got 3 oxygens on this side. Oh no, it doesn't balance for hydrogen. It does balance for oxygen. So we know that A is incorrect, but in fact the correct answer is D, because if we put 3 for Ag and 2 for H2O, and then we simply balance this H plus here, that gives us the correct balancing. So, and we also need to balance this Ag plus on. So we have 3Ag, 3Ag, we have one nitrogen, and then we have 3 oxygen and 3 oxygen on this side, and 4H plus and 4 hydrogen on this side. And then you also need to make sure your charges are balanced. So on this side we have 1- and 4+, which gives us 3+. And then on this side we have 3+, just because of these 3 Ag+. So our charges balance as well. So therefore the equation is correctly balanced for answer D. Question 4. Which sample contains the greatest number of molecules? So To calculate the molecules in a amount of moles of a substance, we have to multiply it by Avogadro's constant. So, for example, if we've got 140 grams of C2H2, we need to find the moles of C2H2, which are found by dividing the mass by the MR. So we'll do A 140 divided by 2 12s are 24 plus 2, you get 26. If we put that into our calculator, we get 5.38 moles. And you don't necessarily actually need to calculate by Avogadro's constant, but if you wanted a specific number of molecules, you could. But we can just assume that the large number of moles is going to give the most molecules. B is 180 over 28. Sorry, 30. Which gives us 6 moles. C is 240 over 58, which gives us 4.13 moles. And D, so we can immediately eliminate A and C. D gives us 400 over 78, which is 5.12 moles. So we know that it's answer B, which is 180 grams of C2H6. Question 5. Chromium 3 oxide, Cr2O3, is reduced to chromium by heating with magnesium. What is the minimum mass of magnesium required to reduce 11.4 grams of chromium 3 oxide? So first we want to work out the number of moles in 11.4 grams of chromium oxide. We do that by the same calculation as before, so 11.4 grams divided by the MR of the, so 52 times 2 plus 16 times 3 is 152 grams per mole. So 11.4 divided by 152 gives us 0.075 moles of Cr2O3. Then we need to work out the ratio in which they're going to react. So we know that it's being reduced. So let's try and write an equation. Because this reduction, you need H plus ions. And Cr2O3 typically react to form CrO4 2 minus. So if we were to assume that they react in a 1-to-1 ratio, we would have 0.075 mole of Mg, which is, we can calculate the mass, so we multiply it by 24, so we multiply it by the MR, which is 24.3, (1.82 grams). That's not correct. So our ratio will actually be 1 to 3. because if we were to balance, so I won't go through it, but if you need to balance for charges and balance for atoms, and then our ratio is 1 to 3, and then that gives you an answer of D. So question 6. A student is supplied with 100 centimeters cubed of a solution of 0.4 mol per dm cubed magnesium iodide, MgI2. A student plans to dilute this solution so that the iodide concentration is 0.25 mol per dm cubed. What volume of water in centimeters cubed does the student need to add? So the first thing we need to do is work out how many moles of magnesium iodide we've got, which we can work out by multiplying the concentration by the volume. So that's 100 over 1000, because we need to convert to dm cubed, times 0.4 mol per dm cubed, which gives us, when we type it into the calculator, 0.04 mol. And then our second part of the question, the student plans to dilute this solution so that the iodide concentration is 0.25 mol per dm cubed. Note that it says iodide concentration, that's I minus. What volume of water in centimeters cubed does the student need to add? So for each 0.04 mol of MgI2, we're going to have 2 times that amount of iodide ions, because it's going to dissociate in water to form Mg2 plus and 2I minus. So that's 0.08 moles. And that gives us a constant. So we use the equation C1V1 equals C2V2. So concentration 1 times volume 1 equals concentration 2 times volume 2. So we want to work out our second volume. So that's V2 equals C1V1 divided by C2, which is, so our initial concentration of iodide ions is 0.8 mol per dm cubed, times by the initial volume, which is 100 centimeters cubed, but we'd ideally, we'd use 100 centimeters cubed because that's what we're given in the answers. And we want to divide it by our final concentration, which we want to be 0.25. So then we just put that into the calculator. That gives us 320 centimeters cubed. But don't forget that you need to subtract the initial volume, so that gives us 220 to add, which is answer C. Question 7. Which row shows elements in order of increasing first ionization energy? So ionization energies increase across periods and they decrease down groups. So if we look at row A, we've got Ca, then silicon, then phosphorus, then nitrogen. So if we just use our periodic table, Ca is lower down the periodic table than Si, so that first part is correct. P is further to right than Si in the periodic table, so that second part is correct. And nitrogen is higher than phosphorus in the periodic table, so that third part is correct. So then we know that it is answer A. Question 8. Bond enthalpies are given in the table. What is the enthalpy change in kilojoules per mole for the reaction below? So when doing these kind of questions, it's usually good to draw it out, but since it's only 1 mark, we'll try and save some time. And so we know that we'll have 4 HS bonds in the first part, and we'll have 3 oxygen bonds, and then we need to, so enthalpy change is the sum of the bond enthalpies of the reactants minus the sum of the products. So we're going to have 4 SO bonds and we're going to have 4 OH bonds as well. So then if we just do this using the table, being really careful when we punch it into the calculator, I find it sometimes helpful to just do the first part, then write it down, then do the second part. That helps keep it simple on a calculator. So 4 times 346 plus 3 times 498, which is 2878, minus 3980, which is minus 1102, so that's B. Question 9. An equilibrium system is shown below. So we can see we've got this, which represents equilibrium. CO plus NO2 goes to CO2 plus NO. Different amounts of CO, NO2, CO2 and NO added to 4 containers as shown below. Which container would have the largest concentration of CO at equilibrium? So you can see straight away that with A, you've got 1 mole of each reactant and no moles of product. So the equilibrium is going to shift to the right. But with B, you start with 1 mole of CO and 0 mole of NO2, and you start with 1 mole of CO2 and 1 mole of NO. So equilibrium is going to shift this way, but since we already start with 1 mole of CO, it's going to increase above. So the concentration of CO at equilibrium is going to be higher than the concentration of NO2 because we have a higher initial mole of it. In this part C, there's a higher concentration on the left than the right, so equilibrium is going to shift this way, so it's not A or C. And then with D, equilibrium is going to shift this way, but we're starting with 1 mole of NO2 and 0 mole of CO. So compared to B, we're going to have a higher concentration of CO at equilibrium. So it's answer B. Question 10. An aqueous solution of ethanoic acid, CH3COOH, has a concentration of 0.5 mole per dm cubed. pKa for CH3COOH is 4.76 at 25 degrees C. What is the pH of the ethanoic acid solution at 25 degrees C? So we can calculate Ka by doing 10 to the minus 4.76, which is the pKa, which if we put it into the calculator gives us 1.73 times 10 to the minus 5. And then to calculate Ka, you do this equation. But we can assume the concentration of H plus is equal to the concentration of the conjugate base, CH3COO minus. So it's just H plus squared. And then we need to rearrange to find the concentration of H plus. So it's going to be equal to the square root of Ka times CH3COOH. So it's the square root of 1.73 times 10 to the minus 5 times our concentration of COH, which was 0.5 mole per dm cubed. Which, if we put that into the calculator, gives us 2.94 H plus concentration at 2.94 times 10 to the minus 3. And then to find the pH, we do the negative log of the concentration of H plus, which is 2.53, which is answer A. Question 11. The feasibility of a chemical reaction depends on the temperature and the signs of delta H and delta S. So delta H is the enthalpy change and delta S is the entropy change. Which row has signs for delta H and delta S for a reaction that is feasible at high temperatures but is not feasible at low temperatures. So delta G equals delta H minus T delta S. So reactions are feasible when delta G is negative, or delta G 0 is greater than delta G. So to be feasible at high temperatures, it must have a positive delta S and a positive delta H, but not at low temperatures, because if you had a low temperature and a positive delta S, or entropy change, then your delta H would be greater than your your value of T delta S. So delta G would be greater than 0, which means the reaction is not feasible. Question 12. Two redox systems are shown below. Which species in the two redox systems is the strongest oxidizing agent? So an oxidizing agent is the species that is reduced. So in these equations, so you need to look at these values, the cell potentials, and this cell potential is positive and this cell potential is negative. So our strongest oxidizing agent is going to be, as you can see, C2+, because the more positive the cell potential, the stronger the oxidizing agent is. So in this equation, C2+ is being reduced, so it is the oxidizing agent. Question 13. Which statements explain the trends in boiling points down the halogens group? The induced dipole-dipole interactions, London forces, become stronger. The covalent bonds become stronger. The permanent dipole-dipole interactions become stronger. So down the halogens group, we know that part 2 is incorrect because the covalent bond strength does not change down the group. And they do not have permanent dipole-dipole interactions because they're non-polar molecules, because there's no difference in electronegativities between two atoms which are the same. So there's no permanent dipoles. So we only have London forces. So we know that the answer is D. Which statements about a molecule of ClNO is correct? It is a polar molecule. It contains 6 lone pairs of electrons. It has a bond angle of 180 degrees. So we know that 1 is correct because O is highly electronegative, so there's going to be a dipole there, and Cl is also highly electronegative, but oxygen is more electronegative than Cl, so the dipoles won't oppose and you'll have a polar molecule. This dipole here won't be cancelled out. And part 2, it contains 6 lone pairs of electrons, so if we just draw them out and consider where they might be. So we have 4 electrons in this bond, this double bond, so that leaves us with well, for starters, you know that chlorine is going to have 3 lone pairs because this single bond will only have 1 electron from it and 1 electron from the nitrogen. Then if the nitrogen gives up 2 electrons to this double bond, that leaves it with 1 lone pair. And then if oxygen gives up a pair of electrons, that leaves it with 2 lone pairs. No, sorry. 1 lone pair. So then it gives us answer B. Because part 3 is incorrect because of this lone pair, which because you do have two bonded areas, but because of the lone pair, that decreases the bond angle, so it's no longer 180 degrees. Because lone pair electron repulsion is stronger than bonded pairs. Part 15, NH4FeSO42 with 12H2O is a hydrated double salt. The student analyzes this double salt using test tube tests. Which rows give correct results for the stated test? Reaction with cold NaOH, green precipitate. Reaction with BaNO32, white precipitate, so that indicates SO42 minus ions. And this indicates Fe2 plus ions. And reaction with warm NaOH in 3 gives a red-brown precipitate and an alkaline gas. So that indicates NH4 plus ions. So the answer is C, because we don't have Fe2 plus ions, we have NH4 plus and Fe plus and Fe3 plus and SO42 minus ions. Using Avogadro's rule. So we get answer C because only 2 and 3 are correct. Because we do have SO42 minus, we do have NH4 plus, we do not have Fe2 plus. So 16a. This question is about magnesium and magnesium halides. Magnesium has metallic bonding and is a good conductor of electricity. Describe with the aid of a labeled diagram the metallic bonding in magnesium and explain why magnesium conducts electricity. So we need to label our diagram. Include correct charges on the particles in your diagram. So when we draw metallic bonding, we'll draw our ions as large circles. We want to do at least a 2x4. You could probably do a little bit more just to keep the examiner happy. And these will have a 2 plus charge because it's Mg2 plus. And then we'll label that Mg2 plus. And then we'll have our electrons as minus symbols. The easiest way to draw them. And we'll label them E minus or electrons. And we need to explain the metallic. We need to explain why magnesium conducts electricity. So magnesium has delocalized electrons, outer shell electrons, which are mobile. Part B. The 12 successive ionization energies of magnesium are shown in table 16.1. Write an equation to represent the fourth ionization energy of magnesium. Include state symbols, so that's very important to include state symbols. You won't get the mark because the definition of ionization energy, or at least the first ionization energy, is the energy required to remove electrons from one mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. Or in the case of fourth ionization energy, the energy required to remove 1 mole of electrons from 1 mole of 3 plus ions to form 1 mole of 4 plus ions, which are gaseous. So we'll go from 3 plus ions to 4 plus ions, and we have to balance the equation using an electron, because that's what ionization energy is. It's the loss of energy for the loss of an electron. Explain how the successive ionization energies provide evidence that magnesium is in group 2 of the periodic table. So if we go back and look at the ionization energies, the evidence that we've been provided with, we can see there's a small jump from 1 to 2 and a large jump from 2 to 3, and then small jumps. So that shows us there, small jumps afterwards, so that shows us that the large difference between 2 and, that's the evidence that there is a large difference between 2 and 3, because the electrons are being removed from a lower energy subshell. Part III, electrons occupy orbitals. In table 16.2 below, add a tick below the ionization numbers that are responsible for removing an electron from a full orbital in a magnesium atom. So I always just find it helpful to draw out the orbitals using this arrow model. So that's our first orbital. We can use the periodic table to help us do this. Second 2s orbital. Higher energy. Sorry, terrible drawing. So Mg has a full 2p orbital and then has a full 3s orbital. So our first ionization number is going to be from a full orbital, so this one. So we can tick that. Then our third, as we can see down here. And we have to remember that when you're filling or emptying orbitals, the empty orbitals fill first, so like this. When I drew them incorrectly. So you'd first go like this, and then you go like this when you're filling or removing. So when you're removing, you would go like this. You lose that, and that, and that, and then that, and that, and that. So that means that we have 4 and 5, but not 6, and then 9 and 11, because these orbitals down here are still full. Part CI. The enthalpy change of solution for magnesium fluoride, MgF2, can be determined indirectly using an energy cycle based on the enthalpy changes below. So we're given the lattice enthalpy of magnesium fluoride, we're given the hydration of magnesium ions, and the hydration of fluoride ions. Explain what is meant by the enthalpy change of solution. So enthalpy change of solution is the enthalpy change for 1 mole of a compound, or you could say solute, dissolving. That's literally all it is. And so part II, on the dotted lines, add the species present, including state symbols. So we're going from Mg2 plus gaseous and 2F minus gaseous down here to MgF2 solid. So that is our enthalpy change of formation. Also, no, sorry, our lattice enthalpy. And then we're going to dissolve it, so that's going to be our enthalpy change of solution. So that will make Mg2 plus aqueous and 2F minus aqueous. So that means that we have our enthalpy change of hydration. It shouldn't matter which one, actually it might matter because you've given the values. So we can see that the enthalpy change of hydration of magnesium ions is greater than the enthalpy enthalpy change of hydration of fluoride ions. So we'll do the enthalpy change of hydration of fluoride ions first. So we're going to still have Mg2 plus gaseous. We're going to have 2F minus aqueous, because we're hydrating it, and then this is our H hydration of Mg2 plus. Part III, calculate the enthalpy change of solution of MgF2. So, the enthalpy change of solution of MgF2 is equal to our lattice enthalpy. So when you're doing enthalpy cycles, you need to follow a route to get to the value which you want, and we want the enthalpy change of solution, which is down here. So our route is going to go like this. So we're going to need a positive value for ΔH early because we're going against it, going against this arrow. So we need to do this. And then we're going with the hydration arrows, so that's 2 times the hydration of fluoride ions, which is minus 506, and only what we need to remember to do 2 times because we have 2F minus in our balancing. And we're also going to need then our hydration of Mg2 plus, which we just have one of, which is minus 1920, which gives us a value of, when we put it in the calculator, minus 6 kilojoules per mole. Part IV, the enthalpy changes of solution of the magnesium halide show a trend from MgF2 to MgI2. So, enthalpy changes of solution from MgF2 to MgI2, so that's going down group 7. Explain why it's difficult to predict whether the enthalpy change of solution becomes more exothermic or less exothermic down the group from MgF2 to MgI2. So more exothermic means more negative, and less exothermic means less negative. So down the group, we know that the ionic radius of our halide ions is going to increase. So we can just put that. And then we also need to consider what that means for lattice enthalpy, because when we're calculating our enthalpy change of solution, we're accounting for our lattice enthalpy and our hydration enthalpies. So that means that our lattice enthalpy, or ΔHLE, becomes less exothermic. You don't say less negative, always say less exothermic down the group. And then it also means that our hydration enthalpy becomes less exothermic down group 7. And therefore, it's difficult to predict whether the whether ΔH hydration or enthalpy change of lattice enthalpy will have the larger effect on the enthalpy change of solution. Because when you're calculating it, you are doing the opposites with the lattice enthalpy and the hydration enthalpies. 17a. This question is about D block elements. Most D block elements are also classified as transition elements. Explain why scandium and zinc are classified as D block elements but are not also transition elements. Your explanation should include full electron configurations. So we need to explain why scandium and zinc are not transition elements. So we need to first define what a transition element is, which is an ion. It forms an ion, element that forms an ion, with a partially filled D subshell. And a D block element is where the D subshell has the highest energy electron. Or you would say orbital actually. And then we want to give the electron configurations of Se3 plus and Zn2 plus, because these are the ones that we want to classify as not transition elements. So, because the only ions that you form from scandium and zinc are Se3 plus and Zn2 plus. So, if we write the electron configuration, it gives us 1s2, 2s2, 2p6, 3s2, 3p6. And as you can see, that there's no electrons in the D subshell, so it can't be partially filled. And then Zn2 plus. And then we need to just write our little explanation for that. So D subshell is empty. And then Zn2 plus, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And the D subshell is full, or not partially filled. Compound A is a hydrated chromium-3 salt with a molar mass of 608.3 grams per mole to the -1, and the following percentage composition by mass. A student dissolves compound A in water. The resulting solution contains a complex ion CrH2O6 3+. The student mixes this solution with aqueous sodium ethane diiodate Na2C2O4. A ligand substitution reaction takes place, forming a solution containing 3 stereoisomers of a complex ion B of chromium-3. Complex ion B is the sixth coordinate and contains 2 ethane diiodate ligands and 2 water ligands. The ethane diiodate ligand is the bidontate ligand shown below. So, a lot of information to digest, but let's break it down. So, we've got our molar mass here, which we can use, and our percentage compositions by masses, which we can use to find the empirical formula. We're dissolving compound A in water, so we're adding H2O, and the resultant solution contains the complex ion CrH2O6 3+. And we've got our ethane diiodate coming in, which is, we know the bidontate ligand because it has these 2 oxygen negative ions which are going to can form coordinate bonds to our central transition element. So our bidontate ligand, how do we define that? Well, a bidontate ligand donates 2 electron pairs to a metal ion. Forming 2 coordinate bonds. And then we've got a long answer question. So, determine the formula of A and B. Write the ionic equation for the ligand substitution and show 3D structures for the 3 stereoisomers of B. So, we'll answer this question and then I'll go through it. So, break down the question. So, sorry. Determine the formula of A and B. Write the ionic equation for the ligand substitution and show 3D structures for the 3 stereoisomers of B. So, we're going to need to use our information from the question. So we've got our empirical formula here. Well, we can calculate our empirical formula from this information. So use the table mass, moles, simplest, and empirical. And then we've got CR, H, O, and S. And CR is 17.1%, H is 3.94%, O is 63.13, and S is 15.83. So let's find our MR value of CR, which is 52. So we're going to divide that by 52 and divide H by 1, divide O by 16, and divide S by 32.1. So that gives us 0.32, 3.94 is going to give us 3.94. Oxygen, we've got 3.94 again, and sulfur we've got 32.1, which gives us 0.49. So CR is the smallest, so we're going to divide them all by that. So that is 1 for CR, and then for H it is 11.9, which we can round up to 12. For oxygen it is 11.9, which again we can round up to 12, and for sulfur it is 1.5. So then we need to multiply by 2 to get 3, and do that the same for all the others. So then our empirical formula is CR2 H24 O24 S3. And then we know that our MR is 608.3 grams per mole to the minus 1. So then if we just calculate what the empirical formula MR is, should be equal to 608.3. Always while you're working. (608.3). So our empirical formula is equal to our molecular formula. And then that is our formula of A, which I like to circle to make it obvious to the examiner. And then we know that compound A is a hydrated salt. So if we account for all of the water, the hydrogens, that gives us 12 H2O. hydrated salt formula, but that leaves us with 12 oxygens. So, and we've got 3 sulfur atoms, and the only way to so if you divide 12 by 3, that gives you 4. So you must have SO4, but yeah, I must have 3 lots of it, and then it's just Cr2 in front of that. So that's our formula of our hydrated salt. That's also A. And then, so part B is our complex ion. So when it's dissolved in water, we get CrH2O6 3+. But then our ligand substitution reaction takes place where 2 of the ethanediol ligands and 2 water ligands remain. So B is going to have the formula CrH2O2 with our 2 water ligands and C2O42. And each of these ligands, these C2O4 minus ligands, has a negative charge. So we have a Cr3 plus on, so that gives us a -1 charge. So they each have a 2 minus charge, so that gives us a minus charge because they each have that negative oxygen. They have 2 negative oxygen ions. And then our ionic equation. So we're going from CrH2O6 3+, and we are adding 2 C2O4 2-, forming our complex ion B. And we're going to remove 4 water molecules. And then we need to draw our 3D structures for the 3 stereoisomers. So we're going to have a cis and a trans stereoisomer. So if I draw the trans first, because for the cis stereoisomer we're going to have optical isomers, also known as stereoisomers. So draw our water ligands, and then our ethane diet ligands. You can draw them skeletally to make it easier. Make sure you draw in 3D. And then our overall negative charge. And then we'll have our cis stereoisomers. So got this one with our water molecule here, and our water molecule there and there, and our ethane diet ligand here. And another ligand here. And then our optical isomer of that is just the mirror image. So remember the definition of optical isomers. They are non-superimposable mirror images. Yeah, we're going to leave the live stream there, so thanks for watching, and be sure to check out my other videos. I've got lots of tips and tricks and exam question walkthroughs to help you achieve success in your chemistry A-level. You can also check out my website to purchase my A-level chemistry notes, or to book tutoring sessions to boost your A-level chemistry grade. Thanks for watching, and